Hur. He received his PhD in 2009 from the University of Cambridge. And then he spent some time as a postdoc at IRIF in Paris and then at MPI in Saarbrücken. Today he's a professor at Seoul National University, where he's leading a group of people focusing on formalization using the rock-proof assistant of software used to produce and verify software. And he made an impressive amount of contribution in that field. I especially remember when he did some work on improving the semantics of pointers for the COMCERT-C compiler. And he also was involved in other projects related to the semantics of low-level languages, to relax memory concurrency, to separate compilation, and to program logic. And today he will tell us about a new verification tool called CRIS. So please.
Okay, thank you. Thank you for the introduction. And so today I will present a notion of imaginary spec. It's really similar to imaginary numbers in mathematics. So now we can say that we also have an imaginary spec similar to imaginary numbers. So this power of, and I will show you the power. So using the imaginary spec, actually we can merge, inherently marry two approaches in verification: simulation relation and separation logic. So simulation relation case, usually it proves refinement between two programs. So the spec is given as abstract program, and the implementation's behavior, the I/O behavior, matches with the spec's behavior, and then used by COMCERT, Certicos, SAL4, and some verification project. Whereas the separation logic is more program logic style. So spec is given as a pre and post condition, and the goal is program does not go wrong, or basically safety guarantee. But it provides very fancy modular reasoning principle, frame rule, and also separating conjunction, and so on. So there is a main tools based on separation logic. So using the imaginary spec, we can merge them really nicely, and also more, not just merging. We can get something new, okay? So anyway, so we can marry them. So yes, using imaginary specification. So what's the imaginary specification? First, like in the mathematics, you have real numbers, and you can extend the real numbers into imaginary numbers. So, and the power is that it may make your proof easier. For example, when you prove cosine square plus sine square is equal to 1, we know that cosine x is equal to this imaginary number representation. Then, once you turn it into imaginary numbers, you can do just a polynomial computation. Then you can get 1. So it makes your computation easier, right? So similarly, we have just a normal notion of a specification, and I will extend it into imaginary spec. And then it will have a similar role. So in general, we will prove that by linking many implementations together, real implementation. So this orange color is a real spec. And then I want to finally prove that some top-level real spec. And then I want to prove this refinement as an end-to-end goal. But we can decompose this proof into multiple different directions, horizontally and vertically in many ways. And then the thing is that in the middle, if we use imaginary spec, we can decompose this proof. So even using the imaginary spec, this in the middle spec can subsume all IRIS style, IRIS separation logic predicates and simulation style, all kinds of operation, I/O, everything can be specified in the imaginary spec. So, so that's the goal. And okay, so first, let me tell you the definition of imaginary spec, which is not very complex. First, the real specification, I would say, basically operational semantics with natural operations, natural non-determinism, so which people call demonic non-determinism, but I think in this context, I will call real non-determinism. And so the real choice is, for example, if you choose X, choose from the set X, then you get possible values, and then you do continuation, right? And then the behavior of this program is the union of behavior of each continuation for each value, each chosen value, right? So that's a usual kind of operational semantics, and this is kind of how usual machine in real world works. It can make some kind of choice, non-deterministic choice, and then it performs. But imaginary spec has something else, some different mechanism, which is people call angelic non-determinism, but in my context, I will call imaginary non-determinism because the purpose is different. And here, so I call take X. So this is also non-deterministic choice. Take X, and then you have a continuation for each value. But its behavior is an intersection of each continuation's behavior, not union. It's a duality, right? So, and then there is no such machine. It's hard to implement such a machine in real world. But anyway, so let me give an example. For example, this program only having real non-determinism, real spec. So you choose from 1 and 2, and then print C. Then its behavior, possible behavior is set, print 1 or print 2. Two possible behaviors, right? And then 2 and 3, then you have print 2 or print 3, right? You have two possible behavior. But now I will use imaginary spec. For example, you take from true and false, imaginary way, and then if B is true, I perform this first program, otherwise second program. Then the behavior of this program is just printing 2, because only print 2 occurs in both branch. Print 1 occurs only in one branch, so it's ignored. So this is the semantics of imaginary spec. So this is imaginary because it's hard to implement this kind of machine in real world, because in order to print 1 here, you have to know that the other branches, all execution you have to know. So it's a kind of basically a halting problem, even harder than halting problem. So it's kind of impossible to implement and there is no such machine in real world. But in the imagination, we can think of such a machine. We can mathematically define and then use it to specify things, okay? So now I will give you some nice example which motivate this imaginary spec. So this is a simple program. Let me first explain. Okay. So this module cell has a local storage, only accessible by the functions in this module. Let's call it current value. And then set function is simple. Just invoke some unknown function input. The input function may get input from the user and then return it, or maybe do something else. But anyway, this is an unknown function corresponding to input conceptually. And then you store the value into CV. So set function changes the current value, but via this input function. And then get function just return the CV. So this is some simple, silly library. And then the main function may use this library. So cell.set. So cell.set just set the value, but via input function. And then foo.foo, another unknown function you invoke. And then you invoke cell.get, and you get value and then print y. So this is some simple program. Okay. And then, so in this case, if you know that foo.foo does not invoke set in the middle in this point, for example, so in other words, if foo.foo does not interfere in my execution, then I can abstract this program into this program. So here, just so you eliminated the invocation to set function and get function, just to directly invoke this input function, and then invoke foo.foo, and then print y. So this program and this program's behavior may be different if foo.foo interfere in the middle, right? Because this code is directly print the value you receive. So even if foo.foo invokes set function, the value, the printed value will be the value you received, the first value you received. But here it will be different because foo.foo can change the value, so the value you print may be different from this one, right? So I want to verify this one, assuming that foo.foo does not invoke cell.set, okay? But in a very, very extremely modular way, okay? So then, first what you have to do is you have to verify this cell library separately, completely separately, independent from the user code, right? Okay, then let's verify this cell module. Okay, set and get function. What would be the spec of this set and get? So natural separation logic spec, one try might be something like this. So this cell X is in separation logic some kind of a resource predicate, and then it can be as kind of points to predicate, and it represents the internal state of the module. So cell X, if you have a cell X resource, it means that the cell module has a X value in the current value storage. So if you first, as a precondition, you get cell X, and then if you invoke get, then it's guaranteed that the return value must be the same, the return value must be this X. And then still cell X remains because the get doesn't change the state, right? And then, but set function is problematic here. So okay, I give you cell X. I know that X is there, but what's the post condition? What value do I get? I know that it can be changed, but what do I get? So maybe currently naive approach would be just exist Y, cell Y. This is sound spec, but is it sufficient spec? Can I prove the previous example using this spec? I cannot, because you lost the information that the y is the value given from the input function, right? Okay, so then how can I specify? So I can specify in this way using imaginary spec. So the idea of imaginary spec is arbitrarily mix operational semantics, just the operation and then separation logic assertion. So separation assertion, two kinds of assertion, assume and guarantee, and then and arbitrary code can be mixed and they can depend on each other. So that's imaginary spec. So I can encode this notion of mixing condition and operational semantics in an arbitrary way using the imaginary non-determinism. I will show you. So here, so let's read this spec. So it says that first, take some value x, which corresponds to this x. But this x is not given from the user, because if you get the function, it has no argument. So actually, caller of this module would not give you any value. But this is x is taken in your imagination. You just non-deterministically choose x. Like just you imagine that this value is given from the user, but actually it's not given from the user, but you can imagine that. Okay, so some non-deterministic choice. And then you assume that cell x would hold. It's also in your imagination. You don't know anything about other modules, just in your imagination, you assume. And then you invoke input function and you get y. And then you guarantee that kind of condition, it's a cell y, not exist y cell y. It's a cell y, exactly the y is given from the return value from input. Okay. So exactly the value comes from. So this spec exactly specify that the cell y, the y comes from the input function, result of input function, okay? So that's our imaginary spec for this function. And then the get function, the imaginary spec would be basically same as the separation logic spec. Like this part is a precondition. You take x at x, and then this is postcondition. I guarantee cell x and return x, okay? So, and then this can be actually proven in our tool, and also it's a contextually, this refinement hold contextually. It means that for any, you link these two programs with any arbitrary imaginary spec, including real spec, the behavior is refined. Okay, so that it holds because of the interesting encoding of this assume and guarantee. So that guarantees that kind of thing. And here, encoding is quite simple, and then we can just tell you the encoding, but just briefly because the mechanism is quite simple. So somehow understanding may take time, but for now, just assume that this A does something interesting. But just I will tell you the definition. So given this P is iris prop, and this P is a mathematical proposition. So assume P simply means if P doesn't hold, take from empty set, which means it's a undefined behavior. So it triggers possible behaviors. Okay, it's a top set. Okay, full set. And then guarantee P is if P doesn't hold, choose empty means that it's empty behavior. So if choose false means just the execution disappears. Okay, and then now I can encode the assume over this iris proposition. And then here, the only thing is that we have a global resource where some resource is stored. We have a repository for storing single resource. Okay, so that's a get RESN. So this get RES is a reading from the repository. Put RES is putting new resource. Okay, so that's the only thing, special thing. And then also this get RES and put RES is only accessible via this assume and guarantee. So using interaction tree, we can prevent. There's no way to access this one. This is the only way to access it. So we know that how it's controlled. Okay. So get RES. First, you get some resource from it, and then you, in your imagination, you take a new resource which will be put it back. Okay, MR prime, and then assume that what you have chosen is valid, and then so. You assume that the MR, the newly chosen one, implies the P and the original one. It means that the new one contains both existing one and then new resource that satisfies given P. So somehow, assume P, after assume P, you have more resource, right? And then you put the resource back. And then if you think of this semantics of take, any resource that does not satisfy these two will trigger UB. And then the total set UB is identity to intersection. So the behavior you can just ignore. So the actual behavior of this one is the intersection of MR prime that satisfies this one. Okay. And I will not exhaust. So get RES and then choose new one, and then prove the duality. So it means that this one is the new one is existing one minus P. So existing one should imply the P and then the new one. So new one is conceptually, you take away the P, okay? So that's all. Okay, this is a perfect operational semantics, and it has a proper notion of set of behaviors, IO behaviors, and so on. Okay, so now, using this spec, I can verify this main function. So this refinement does not hold in general. I have to know what the spec of cell get and set get, right? So if this is arbitrary function, this refinement cannot hold, right? So I need the spec. So in this case, I will only use this spec, the gray part, right? So in the verification, when I use this spec, I link the source program and target program both to the spec, and then prove refinement between this linked program and this linked program. And then the reasoning principle for using this spec, that's something completely new in our CRIS work. So we have earlier work, but that didn't support this kind of idea of mixing condition and operation arbitrarily. But here it's possible, and then when I use this one, essentially reasoning principle is just inlining. When I invoke this one, I jump to here and execute it and come back. So I can just treat this code plus conditions as if it's my own, just code. I can just execute it like as if it's my own code. So when I invoke cell.set, I just execute it. So that's all. That's the reasoning principle. So then this spec in an intended way. So okay, let me show you in detail. So first, this source program does not invoke any of a cell function, so I just hide it to make some space, okay? And then I will show you how this proof works in iris proof mode, okay? So first, it's a simulation relation, so we start with the same place, and then in our simulation relation, we can take a source and target separately. We don't need to take both steps at the same time. This is thanks to the FreeSim work, so we use that idea. So, and then what I do is that first, I execute this assume cell 0. Then what happens is that I obtain this cell 0 resource in iris proof mode hypothesis, okay? So I obtain this one. And then I execute this target side, so cell.set. So by inlining, I can essentially jump to here. So my code goes here, and then I will keep executing it. So now I will execute take. And then take, if it occurs in the source side, it's like a really, you are taking some value in your imagination. But if it comes in the downside, the target side, it behaves dually. So it means here you can choose. Instead of a value is given, you can choose. So if you execute it, actually the logic asks you to choose a value. So in this case, I will choose value 0, because otherwise my proof may not go well. So I will choose 0. Okay, and then assume cell x. If this occurs in the source, I'm given cell x, like here. So this assume I was given cell 0 because it was in the source side, but this assume occurs in the target side, then it's a duality. I have to prove cell 0, right? How can I prove cell 0? Because I already have cell 0. So after this one, I proved it, and my cell 0 has gone. So in the iris proof mode, nothing. Okay, it's gone. Okay, now both programs are waiting to invoke input. So now I invoke input, even though it's completely unknown function, I can just invoke simultaneously. It's like a normal simulation relation. I can jump over it because I invoked the same function with the same argument. Okay, and then I can assume that the return value is equal. So that's the logic provide. And then, so let's say the return value is I. Okay, then both the source program and target program has value I. Okay, then I execute the target side. Then I again receive cell I, right? Because this guarantee is a dual. So now guarantee in the target side will give me cell I. So previously I had a cell 0, but after executing this set, now I have a cell I. Okay, so I return. Okay, now both programs are about to invoke foo, which is a completely unknown function, but our logic allows to, if they invoke same function with the same argument, then it's okay. You can jump over it. Okay, and then now the target program also cell.get. I will execute cell.get. Okay. Here, so another important point is that actually foo can interfere you in real world, but in the logic we can assume that foo does not interfere. So that's the power of separation logic. Since I own cell I, the foo does not own cell I, right? So foo cannot invoke cell.set because the cell.set has require as a precondition this cell resource, but I have a cell resource, so no one else can have a cell resource. This is cell is unique in the separation logic resource. So somehow logically I can assume that I can reason locally without worrying about foo. But in reality, foo can invoke it. So that's the power of imaginary spec. So this encoding of take and assume can make sure that if the foo invokes cell set, somehow it triggers UB. So this program trigger UB, so source program trigger UB means that arbitrary behavior can happen. So refinement just trivially holds. So that case is covered by our encoding. But in the logic, you can assume that foo does not interfere with you. That's your intention of this resource. Okay. Okay. Just a second. Okay. Cell.get. Okay. I jump to this one. And then now I take int, so I can choose one. So this time I will choose I. Okay. And then I have to I have to provide the cell I, right? But I have a cell I. So cell I is gone, empty. And then I get cell I back because of guarantee. And then I return I because this value x, I chose I. So I know that the return value is I, right? Return I. So here I know that this y is I, right? So both this one is I, this one is I. So I print at the same time with I. So it's guaranteed that I print same value. So the refinement holds. So this is how this refinement works in our proof mode. I will give a demo in a minute. But okay, that's all. And then now we had two local reasoning about. One is about this module cell, and another is about main function. And I will show you how to compose them together. So first, this one I haven't shown you how to prove it, but it's a very easy proof. But anyway, assuming that we prove this one. And then since this is a contextual refinement, we can compose with this main function implementation. Okay? And then this main function with the spec, we just prove that this one refines the main spec linked with the cells spec, right? And then by transitivity of contextual refinement, we can get this one. Okay? And then since this is also contextual refinement, I can add arbitrary identical context, which is foo. Okay? So this refinement holds. So it means that this holds even when foo interfere you. So if foo does not invoke set, somehow intuitively we know that this refinement holds. But if foo invokes cell.set, then we know that intuitively this one will print first value, this one will print the second value. So it may be different, right? And the only way it's possible this holds is because if foo invokes cell.set, some UB will happen, undefined behavior will happen, right? So I will just check. Actually, that's the case. And then this is not the case in the previous work. CCR, this refinement does not hold, but now new CRIS, this holds. Okay, so this was our previous encoding, and I will just briefly tell you why UB happens. So for example, here at the beginning, so let's execute the only source program, and then I will show you UB happens if foo invokes cell.set. Okay, so and let me execute this assume. So then first, the L0 is given as argument, right? And then I get value from the repository. But in this program, initially it's empty. Okay? And then I can take some cell 0, but actually I can take arbitrary value. But if you take other than cell 0, it's always false here because the P is cell 0, and then MR prime is something else than cell 0, cell 1, for example. Then cell 1 cannot imply cell 0, so it will be false. So you can ignore that. And the only case which survives is cell 0. So you have cell 0, then it means that the repository now contains cell 0. You put cell 0 in the repository, okay? And then if foo invoke cell.set, then it can take arbitrary value, but any value, whatever value it takes, it will trigger UB here. Because, let me execute that here. So for any value x, so you provide the cell x, and then you retrieve the repository from the repository value, which is cell 0 because you just stored it. And then, but you see here, the P star own MR is already false because the cell X and cell 0. So cell cannot have two copies. So it's already false. So whatever X is taken, this triggers UB. So whatever value is taken is UB, so it's UB. So if foo function invokes this function, it automatically becomes UB. So that's why this refinement holds. Even though in the reasoning, I ignore this using the power of separation logic. Okay, so this is a mixture of unknown function call and separation logic and simulation. So this is always also termination. This program must terminate because the spec terminates, right? So if you want a divergent program, you have to put some operation, while star skip or while true skip or something like that. Then you can allow a divergent program. But here it's a terminating program. So in our tool, we support both induction and co-induction to verify those things. Okay. Let me check. Okay, finally, the interesting part is finally, we can eliminate this all assuming which we don't understand, and then get real spec. So this is automatic part. So here, if foo.foo does not invoke cell.set, then we know that every assuming guarantee matches. So our tool automatically check that matching, and then eliminate those things automatically. That's our cancellation theorem. So if foo.foo does, for first, the main function does not invoke this function, so there is nothing to match. And then foo.foo does not invoke this one. If foo.foo does not invoke this one, then nothing to match, so automatically match it. But if foo.foo invokes this function, then what happens is that cell.set has this assume and take part, but there is no corresponding part in this code, right? So there should be equivalent to guarantee there. Then they met, and then they can disappear. But since there is no such thing, if this foo.foo invokes this function, then our cancellation theorem cannot proceed. But if it doesn't invoke it, then we can proceed it, and we can prove, we automatically get this one. So finally, we have a real spec to real spec. But in the middle, we use the imaginary spec to specify something interesting, okay? Okay, so let me see. So what time? So until 10, or I have half an hour? Okay, I think it's good. So I think this is a somehow important part so far, and the main ideas. So finally, we have by transitivity, we have this refinement, okay? And then I will show you two more examples of interesting specification using imaginary spec. So one is a logical atomicity. So in IRIS or other separation logic, you can encode the logic atomicity in a certain way, but in imaginary spec, it can be very directly, easily specified. So for example, assuming certain atomic function, and there is some implementation, and this is spec, then usually what happens is that the function executes in multiple steps, and at some point in the middle, atomic action somehow, like a CAS, if it's CAS, the CAS happens in the middle of the function code, right? So, and then, but the problem is that the resource that is needed at the point of atomic point should be given by the user at the beginning of the function, because in IRIS, the pre and post condition is really pre and post condition. It's not middle condition. So you have to provide something interesting encoded resource that guarantees that you have ability to acquire the wanted resource in the middle, something like that. But here, you don't need to do that, because we can operationally express atomic section. So this scheduler.yield is some kind of, later I will show you, but it's adding concurrency to the model. So this is interference point where some other thread can be executed, right? So operationally, I know that this part is atomic section. So this spec as a single yield and single yield means actually in the implementation, you may have many different yield, but we can abstract into 3 sections. Before the atomic section and after atomic section. And then precondition, usual precondition is given here, and post condition is given here. But the condition you need for the atomic update or whatever, that's given in the atomic section. So I can control the point where I require assuming guarantee. So the assuming guarantee does not need to be always pre and post condition. Anywhere you like, you can put the condition. Then you don't need any encoding. You just put what you want, okay? And then we already have examples verified in COG, and with some concurrency example, it works perfectly, okay? So you don't need any fancy encoding. Another thing is interface abstraction. So you can also abstract even argument and return values. So thinking about some linked list example where the argument is a 64-bit pointer values, okay? And then you take a pointer value and update linked list kind of thing. So let's say add a front function, which it takes pointer and then value, and then it add this value into the list, okay? And then the spec, direct spec would look like this. Takes pointer and then value, and in your imagination, you choose corresponding mathematical list, and then you assume some kind of point to predicate, this point to predicate this one, and then you have a code which is purely working on the mathematical list only, without mentioning any P. Okay, so here, as LST prime, new prime will be mathematical append cons function, and then you choose corresponding physical address, which points to the new mathematical thing, and then you return. That can be your spec, and then you can verify your implementation in C against this one. That's possible. Actually, we have more complex examples. But and then the user of foo will have some code which is purely some code working on mathematical list only. And then at the invocation time, you have to convert the list into physical pointer. and then pass it to the function, and then get the physical point, and you convert it back to the mathematical list, and then you do every working on only mathematical list, okay? And then this kind of conversion we call virtual argument and physical argument. So here, this is all kind of generated code, not user need to write down. Using the interaction tree translation function, we can generate this code. So this is a virtual argument, and this is a physical argument because it's physically given. And this is a physical return value. This is a virtual return value. Okay, so the user, and then our cancellation theorem automatically delete physical and the conversion everything, and you get only the code with the virtual argument only. So this function take a mathematical list and return it. This function pass mathematical list and get it. So we know that the behavior, linked programs behavior is same as linked programs behavior in C. Even though in C you pass the pointer values and then this spec you pass the mathematical list, their IO behavior are equal. Okay? So that's just the result of our tool. This can be done automatically. So we have a generalized cancellation theorem, which it does also cancel out matching assuming guarantee, but also it cancels out the matching conversion between physical and virtual argument, virtual return values. So all canceled out, and you have only the virtual code only. Your top-level spec will be much more cleaner than implementation. Right? You can specify your program in as a mathematical function or whatever. Okay. So that's all. So that's a key idea. So at least I'm done key idea. So but there's another half of key ideas. But anyway, so maybe let me really briefly show you the demo. So it's our system. It's a really like it's in the IRIS proof mode. So this say that main function, main module and cell IO module. This is the library module I linked together, and main implementation and cell A. So you see cell A. So this is a spec of a cell. This is also spec of cell. This is a spec of main. This is implementation of main. So as I showed you before, I linked the program together and then verify the refinement. So then what I have is here. This is the source program, which is the both imaginary spec. This is a target program of main, and then we have some IRIS predicates and so on. And then if you execute, so here you see in the code we have assume. This is the code, right? So we can operationalize assume and guarantee. So everything is operational semantics, and then we can take steps. Steps L means steps in the source side. And then this is IRIS command. And then I get, let's see. So I get L0 here, right, in IRIS. So I will not follow everything because this is exactly matching with what I explained previously in the animation. So this is a stepwise experience. So inline. So inline is really jumping to the cell module. And then I execute. And then at some point, I will have a cell I. Okay, I lost the cell because in the middle I lost cell, and then I invoke some same function at the same time, and so on. At some point I will have a cell I. Okay, so I will maybe stop at this point. Okay, now I have a cell I, right? So something like that. So I can complete following the same steps. I can complete the proofs. Yeah. Anyway, so let's go back. So it works really like IRIS. So it builds upon our earlier tool, CCR, which is similar to this one, but doesn't support this arbitrary mixture of conditions and operational semantics. So CRIS is somehow much more advanced than CCR. And also we employ a lot interaction trees. Without interaction tree, I couldn't imagine how to implement this one. And also without IRIS, I cannot imagine how to implement this one. So we directly use IRIS proof mode, just import it, or resource algebras, we just import it. We don't define, we just import it and use it, okay? But our theory is different from IRIS, so we don't use the step indexing. It's a really simulation relation. So, but we can support a lot of features of IRIS without step indexing. So we can support the ghost location exactly the same way. So user wouldn't feel difference. You don't see any difference. And they're also opening and closing invariant via fancy update exactly the same way. And logic atomicity slightly different way. But also we can support, we believe we can support the same encoding. Just we haven't tried. And then higher order predicates in a different ways. Instead of using step indexing, we can do my earlier work called the parameterized by simulation. So the key idea is that we can use parameterization to handle higher order or to solve cycles. So here we use similarly, we somehow parameterize over spec, then we can support higher order predicates. So we have a Landin's NOT example and other some higher order examples. And so far, I don't see any problematic example. But probably since this is not purely higher order like Iris, there might be certain challenging example, but I don't know yet. So all kind of example I can imagine is okay, but there might be a problem. But yeah. But the important thing is that if you have step indexing, the transitivity does not hold. So we cannot, we have to give up step indexing because we want to have a contextual refinement which is transitive, right? So in order to have transitivity, absence of step indexing is important, okay? Okay, and then, I think it's a good timing. So, and then the second part of talk, I will focus on how modular our system is, because as I have shown you, each module has its own operational semantics. It's independent from other module semantics, right? So even we could link with this real spec and the imaginary spec. So this operational semantics and this operational semantics are very different, but we can link them together, right? And then we can pass arbitrary mathematical values around between them. So this is very powerful, and I will show you how to do that. So here, yes, we allow the C programs or OCaml programs or specification or model, whatever models, everything is expressible here as an interaction tree. And then we have a general tactic which works for every interaction tree. So even our general tactic works for C-Lite code, okay? And then it works under, also our verification is stable under arbitrary contextual module. So the verification result is very strong. It's composable with anything, right? So using this, what we can do is that we can encode a lot of meta-level features and concepts as a user-level module. So I will show you maybe 10 kind of examples, and it's really covering a lot of things, okay? So for example, we can add this memory module into the system, but without changing, the underlying system does not have any notion of memory. But we can add the memory system by adding memory module implementation. So this real-world real spec is that it has an interface with a malloc-free write, read, the comparison, and some other things if necessary. And it all specified as an abstract operational model written in interaction tree. So it's a mathematical memory model. And then here, the spec is some abstract spec with assuming guarantee, which will look almost identical to separation logic assuming guarantee. And I can prove this refinement as a user-level proof mode. As I showed you before, just in the user-level mode, the Iris proof mode, you can just prove it. Then you have a memory now. If you invoke these functions, you can use this spec for your reasoning. We can also extend with the scheduler. We can add the concurrency, right? So the scheduler module will have a spawn, join, yield, get TID. So we already implemented it. And it's specified as an abstract operational model which makes interleaving between threads. And also the scheduler algorithm, you can choose completely different ways. Either fair scheduling or unfair scheduling you can do. But for scheduler, we need some primitive support. So CRIS provides primitive operations for basic interleaving. So it's a really primitive basic interleaving features. Then this scheduler can use it to implement your wanted scheduler, any kind of schedule algorithm you can implement. And then you can give assuming guarantee pre and post condition for each function as a spec. And then you can also prove it in user mode. Okay? You just add this user level module, then you have now concurrency. So you have a memory module plus scheduler module. If you link together, you have a normal concurrency. Okay? And also, even you can have network model. So we also implemented this interface, so can send, receive, listen, whatever, with just specified as some mathematical operational model. And currently, we only have UDP, but you can also define either TCP or both. It's okay. Just I think, if I remember correctly, we just have UDP model. And then you can give also pre and post conditions, and then you can also prove it in a user level proof mode. And you have now network plus scheduler, then you have a distributed system. Also, even you can have a scheduler for network scheduling, and each node can have a memory plus each node's concurrent scheduler. Then you can have a distributed system with a concurrent execution in each node. Okay. Now we also have a weak memory, because I also worked on weak memory quite a lot, so I know weak memory well. So we also implemented weak memory. So weak memory model here, and the weak memory spec here. We haven't verified this refinement yet. It's in progress. But it can be basically done in user level proof mode. So this model we based on our previous, my previous work, VIC11. And so this can be done, okay? And then weak memory plus scheduler, then you have a complete weak memory scheduler, and you can reason about weak memory programs. Okay, COMSOLT memory model. So we can also have a COMSOLT memory model here. Malloc free, write, read. It's really a COMSOLT memory model. So we just directly use the COMSOLT memory model definition exactly. We didn't change it, just the same definition. We just wrapped around it to make it to interaction tree style. So they just very shallow light translation from CLI memory definition to the interaction tree. So it's exactly the same memory model. And then we can add assume and guarantee for this memory model. And then actually we did more than that because in this coming Friday, one of my students, Yonghyun Kim, will present at Purple, which is a COMSOLT cast, which support integer point casting. So it's a fully preserving all COMSOLT passages. We didn't miss anything. It's a full COMSOLT, but with the point integer casting. So here we have a model with the point integer casting. And we have a logic with the point integer casting. And so we also, I will tell you, so we verified the XOR linked list. Anyway, that's possible. And this is already done. So this can be done in user level proof model. And then now we have a C-Lite memory model. And then we also have a C-Lite code. So what we do is that given C file, we use a C-Lite parser to generate C-Lite code in core. And then we define the simple translation that from C-Lite code to interaction tree version of C-Lite. So also this is a shallow translation. We use original definition exactly same way. We didn't redefine. It's the same definition, just in the interaction tree style. And we call it C-Lite plus because interaction tree is better, so it's plus. But anyway, basically same. It has a go to, switch, break, continue, every feature. We didn't miss anything. It's exactly the same definition. And then you can imaginary spec with your own imaginary spec, and you can verify. So we verified, of course, user level proof mode. We verified XOR linked list, proper XOR linked list implementation. We fully verified, and also we linked the result, combined it with the COMSOLT result. So we have end-to-end verification from the top-level real spec down to real assembly code of C-Lite. Okay, that's our result. So this is done. So I will give a very quick demo on this if I have time. Okay. And also another point is actually the working on C-Lite is quite pleasant. So so our general tactic works very well, and I just added the 20 lines of extra tactic to just handle boilerplate code. And then it's really quite fast enough. I mean, it's not so slow. And then also reasoning is quite pleasant. So we could easily add the program logic for C-Lite, power of program logic to C-Lite easily. And we can do the same thing for other semantics as well. If you have your own semantics, you can just have a shallow translation from your semantics to interaction tree, then everything, you're done. You have automatically, you have a full power over this CRIS, or separation logic, iris power, and then or simulation power and everything you can get for free, okay? And then now more consistent. So also, since this is a termination preserving framework, so we can specify liveness and fairness. So in our previous work, we presented fair operational semantics, which is how to operationally capture notion of fairness. So we also defined the fairness module, which has a single interface function called fair, and which has some operational semantics following this work. And we have also fair module specification, which is LILO. It's a conditional accepted at USLA 25. Oh, sorry, 25. Yeah, it's inconsistent. Yeah. So we can import that specification into here, and we can prove also refinement as a user level proof mode. Then we have a way of specifying fairness, and then way of reasoning about fairness and everything we get. Okay. So we can now specify liveness, fairness, and safety in one go. Our specification talks about everything. Okay, and then we can verify our verification, actually verify, respect all the features, okay? So, also we can define fair scheduler using fair. So we can change the scheduler module, we can define another scheduler module, which using fair module, you can specify fair scheduler, like no thread is starving, something like that. So you can do that. And then also we can do prophecy. So this is like a halfway goal. So we are very sure that this will work, but even though we haven't completed the proof yet. And the idea is that we can have a prophecy module with the 3 interface, new, resolve, and close. And then the implementation is just simply every function spot is just skip. So invoking new, resolve, close anywhere in your code is completely identical code because it's just skip. But in the refinement, in the spec, you have new resolves close with a certain assuming guarantee, which gives you full power of prophecy reasoning. Okay? And then, but unfortunately, this refinement only holds on the real spec. If it include a take, like imaginary non-determinism, this refinement does not hold. There is a counterexample. And intuitively, somehow we know that that's a wrong reasoning. So what happens is that in our scenario, we always start with the real spec, and then go into the imaginary spec, and then finally jump out of imaginary spec and then go into the real spec, right? So in the first place of lifting from real spec to imaginary spec, you can insert prophecy variable anywhere you want. Because at that point, your context will be all real spec. So you can insert, at the first time of lifting, you can insert the prophecy variable anywhere. It's completely free. There's no ghost code at all. Just you can add it anywhere you like. Then later on, not immediately, later on reasoning in the upward, you can anytime when you want to reason using prophecy variable, you can just use this assuming guarantee. Then it gives you full power of reasoning about prophecy variable. And also this interface is slightly more general than the IRIS's previous work. I mean, we really like it. And then just so we generalize the interface so that we can have more power. But that's not essentially very different. But somehow this refinement without ghost code is something new. And we are halfway through this proof. But the proof is not user-level proof mode. As you see here, it's not normal contextual refinement. It only holds under real spec. And then this proof is very, very complex co-inductive proofs. A lot of co-inductive techniques that we developed, we fully utilize it. Anyway, it's a not easy proof, but we are sure that we can finish it. I mean, we have very clear idea how to prove it, and so hopefully we can finish it soon. So that's almost all. Okay, so I have to stop here. Let's see. So status of CRIS. So we fully developed a CRIS framework. There's no limit at all. It's fully done. And then some of the extension modules I mentioned are completely done, and some are in progress. And also our work hasn't been submitted yet. We are preparing submission. So tool is already usable with many examples. We have many, many examples, but no documentation. So we are not going to release it now. But if you are interested in, I can give a private access so then you can play with it. Okay, so just tell me if you're interested. Finally, a lot of people I have to thank. So for CRIS, so many people, because many students are interns, it includes every intern. But anyway, so it's basically all of my current students. And the CCR is our predecessor, where Yongju and Mingi was the main guy who developed CCR in my group. And then also Michael and Derek helped us. And then Archimage and Consult, which will be presented at Popul on Friday, also these students. And then really thanks to IRIS, interaction tree. That's a really cool tool. Without it, even though we had the idea, we could not implement. We could have not been implemented. But anyway, thanks to this one, and Paco is my own tool for co-induction, but we used a lot. And I just missed one more tool. I thought about it in the middle, but anyway, probably there is more to be used. Okay, thank you. Yeah.
Are there any questions?
Yeah.
So thanks for the nice talk. It looks like a very cool tool.
Yeah.
So what are the limitations of CRIS?
Limitation. Let me see. Somehow it can be a bit slow, and then if we can make it faster, that would be cool. But it's a quite early version, so there is room for improvement. And then also, as I mentioned, the higher order thing. Currently, we don't have step indexing, so if there is a possibility that certainly somehow complex way higher order predicates, we may have trouble to express it. But I don't know any example yet. But maybe there, and then my belief is that there should be a solution. So if we see a challenge, then it may not work directly, but should be able to find the solution. But that's my belief. But currently, it's not fully like a truly higher order thing. Okay, yeah.
Hi, thanks for the talk. That sounds cool. So if you want an interesting example for higher order ghost state, check out the Rust Belt lifetime logic.
Lifetime logic, okay.
We're having some fun with higher order ghost state there.
But I think that's use case. Oh, use case I should have mentioned. So we use the use case Neil anyway tool.
NOLA.
NOLA. Yeah. We use the same idea basically here. So didn't he use the NOLA to handle that one?
Okay.
But then we can do it. We follow the same.
I don't know if I don't know the state of.
Okay. Thank you. Anyway, so yeah,
we
can check it.
Anyway, but I had a question. So you had this refinement earlier in your first example. There was this foo function, and you said something about foo can't use cell or something.
Foo shouldn't.
Like, how is this expressed formally? I guess this is a side condition you have omitted on screen.
Good.
Is this like a syntactic check?
No.
Like what does it mean?
Interaction tree, we can do that. So what we did was that in this final refinement, what we did was that given foo.foo function, we just added a wrapper function which makes a call to cell.set to skip. So that in the interaction, it's given as an interaction tree. So you can have a event handler. So you just handle the call to the cell.set. You just intercept, and then just turn it to skip. So we just proved that conversion after that conversion. So that by construction, this cannot call thing. But if this function didn't call it, the handler does nothing because the handling only intercepts that call, right?
Okay, so the chain is like I have this foo module, and then I have foo module wrapped in this like cell hider.
Right.
This refinement, which is where I prove that I'm not using cell.
The refinement between you mean the two? This one, or?
Yeah, I guess I have to prove that my cell hidden foo refines the original foo to show that I can go in the chain, right?
Yeah. You may. But if by construction, if it doesn't occur, I mean, it will be just
should be a simple proof. But and then I have the cell. Okay, this does remind me a bit of dim sum, which also has these fun wrappers that you compose while refining and composing. I don't know, just putting that out there in case someone finds it interesting.
Yeah.
But thanks anyway.
Yeah. Okay.
So I wanted to ask about this cancellation theorem. Like, what exactly do you mean by matching? Like in this example, you have an A but no G. So what's matching?
That's correct. So A is really the initial condition. So that's actually proven by the user directly, and all the other things should match. And A is the only exception, actually. Yeah. So the main function's first condition is the only exception. So that
and how are you getting rid of the cell module?
It's also interaction tree thing, because actually this code is all generated by this. The code that is intended to be deleted is not written by user. So user has a certain event, then the event handler can generate that boilerplate code, and then later the cancellation theorem just delete that event using another event handler. Just delete. Not event handler, just you drop the event handler, then you get original code. So somehow this boilerplate code, like this assume and guarantee and take things are mostly generated by the interaction tree event handler, and then also deleted automatically. So that's how we handle the elimination. So without event interaction tree, I don't know how to do that, because syntactic search kind of thing is ugly, right? But yeah.
I just wondered about the automation. So is your tool, if I'm a newbie to this, is it able to somehow automatically hint at which are suitable suitable imaginary specifications? So how to come up with this new annotations? And so once you have these annotations, these steps that are done in this rock proof here, so is this generated automatically for you, or do I have to do this all manually?
Which one all manually? You mean the, sorry, I missed the, text, this one. This one currently manually. Yeah, currently manually. And then, but this is really, our simulation is iprop. iris prop predicate. So this is really just iprop. This whole goal is iprop, but just displayed in a more readable way. So this is everything is iris prop. So any iris predicate automation tool will apply here. It's just simply iris prop, and everything is iris, so that will work. And also another, maybe my vision is that this kind of proof is done by, this is done by me, but after reading someone can do this by reading tutorial and then this one, these simple things. I think LLM can do that too, soon, like really in a near future, because it has a logical reasoning power now. So we can just teach it LLM how to use our tool, and then it can probably prove many things. That's my kind of vision.
Okay.
Hi. At one point, you gave the impression that, or you pointed out that it wouldn't matter what semantics you have. You could. This would be completely general.
Yeah.
But the examples you gave, it seemed mainly for like imperative languages. And would it work for any kind of semantics? You could do the same thing, or does it have to be this pre and post condition logic and things like this?
Oh, okay. So I don't think this tool has any kind of it's a stick to imperative program, because we use the imperative program as examples. But it's just an interaction tree. It can also we have so you can define high order functions in Coq and then verify against it. That's also possible. And also we can encode some kind of OCaml syntax in interaction tree. And then anyway, it's operational semantics. We have an induction, co-induction, and all kind of general reasoning tool we support directly. So I don't think. I think it's similarly. Also, there is a separation logic for functional languages, right? So similar approach we can do. So I don't think there is a fundamental limitation. Yeah.
Does this work? Yeah. So this is, as usual, very interesting work. So about the modularity aspect that you talked about in the second part, I'm trying to get a sense of what that will allow you, what practically you can do when you mix, for example, say, weak memory model module with other modules, because my experience in Iris, at least, is that, I mean, yes, of course, you can build versions of Iris that work with weak memory. We've done that many times, but then it can radically change the kind of reasoning principles that are allowed, right? For example, regular invariants are no longer.
Sorry. For example, what?
For example, invariants, right? Standard invariants no longer.
Sound invariant. Invariant.
Invariant mechanism, no longer is like sound, right?
No. We
need to change. You need to adapt. So I'm curious how you end up.
Oh no.
Like in Iris, you build up layers of new abstractions for given, but I don't see how these would interact.
Okay. So if I understood your question correctly, I think the way we handle invariant, those things are very different from Iris. So Iris has some kind of fixed physical state predicate or something special. But in our case, we don't have such a thing at all. So our resource predicate is not related to physical state or nothing at all. It just goes. It's not related to anything. But you can relate certain predicate into physical state. Physical state here is only module state. So you can, for example, memory module case. So the memory module predicate, for user's viewpoint, it's completely nothing. It has nothing to do with the physical state or anything. It has just a rule of resource algebra. So you cannot have L together, that kind of rule only. It's not related to anything. And only this memory module can relate it to its physical module state. So actual physical module state will be a module local state of this module. So every points to or memory will be defined as a mathematical map, whatever in here. And then you can only relate the predicate into your module local state only internally, and user does not know existence of this one. User only verify against this spec. So it means the user's case, you haven't seen this thing at all. Just existence doesn't matter. You verify against this one, and then this verification guy verifies that actually this spec contextually defines this one. So the connection happens only locally, and then it's by something called IST, state invariant. So it's a module local state invariant we have, which is conceptually correspond to state instantiation thing in Iris. But each module can have its own custom relation so that it's not visible to outside. Does that make sense? Or?
Let's take it offline.
So anyway, the result is that we have examples. It works well, so we can combine anything together. Anyways, yeah, it works so well.
So this pattern of connecting, like rather than using a pre and post condition, using operational semantics or something that looks sort of like operational semantics, seems very similar to using weakest precondition inside propositions. Do you know like how this, like you could also write a lot of these specs in that
okay,
style?
good point. Yeah, that's a good point. And then actually, that's a good question. And then the answer is that the weakest precondition, the condition in the middle is only visible to verifier, not client. Client only see pre and post condition. That's the problem. In our case, client see the middle condition. Client can use. So look at, for example, this spec. This information is visible to the user. This is a reasoning principle to the user. But in the weakest, even if with the weakest precondition, user only see pre and post condition. That's all.
But the pre and post condition could be it could be a weakest precondition of y equals input of cell y. You know, like you could interleave.
But that's implementation code. That's implementation code. So you are verifying against the implementation code.
No, I mean in the spec itself, you could have weakest preconditions there, and that would be a way of expressing these kinds of
I see. I see. Now I get your. So your point is that somehow encoding this whole operational flavor thing as a pre and post condition. Okay. Yeah. That can be that can be another approach, but I don't think it has this full power of vertical composition. So we can abstract program. So actually, the power of this one is really we have a code semi-abstracted. Some code is abstracted at the assertions. Some code are remaining same, right? Like here, the input is unknown function call. So input is not input doesn't have any pre and post condition. Input is just a function call, right? It's a code itself. And so I have a nice example where sometimes network. So actually, this is an ongoing project. You have the distributed system, and then you have ref algorithm, and then each node may have completely different ref implementations. And then the way we verify is that we give a reference implementation, and then we verify the whole algorithm correctness based on reference implementation. And each node, just to prove its implementation, refines the reference implementation. And this refinement even requires a certain pre and post condition about network things and so on. It's not purely like a compiler correctness. So this kind of decomposition is possible, and we can have a multiple decomposition over in various different directions. Okay, thank you. Thanks.
Thank you again. So
okay, thank you.